calculus students, welcome to class. Today we are going to learn about a topic that may sound kind of familiar. We are doing Taylor and Maclaurin series. Now we've kind of been stepping up into this topic for quite some time because we've already learned about Taylor polynomials and Maclaurin polynomials, and so those would be just finite versions. They stop, they don't go on forever, of what we're doing today. And we've also learned about power series, and both a Taylor series and a Maclaurin series are types of power series. So you already know quite a bit about a Taylor series and a Maclaurin series, but as a reminder, our rule for a Taylor series is the sum from n equals 0 to infinity of the nth derivative evaluated at c over n factorial times x minus c raised to the nth power. And that is going to produce the following terms: f of c plus f prime of c times x minus c, does this look familiar, plus f double prime of c times x minus c squared over 2 factorial, plus dot dot dot, plus the nth derivative evaluated at c over n factorial times x minus c to the n plus dot dot dot. So the big difference between the rule that we learned before for a Taylor polynomial and this one is that it ends with plus dot 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 because it goes on forever and ever, and the upper limit on our sigma is infinity. Okay, now if c equals 0, the series is a Maclaurin series. So we can basically use the same rule for a Maclaurin series, just change the c's to zeros. Okay, so I am going to go through the next 4 examples slowly and in great detail, and it may seem a bit repetitive from things we've done before, but there is a reason for that. We are going to find the first 4 non-zero terms and the general term of the Maclaurin series expansion for each of the following functions, and then we're going to express the series using summation notation. So summation notation would be like with the sigma notation. Okay, now here's our first one. It is 1 over 1 minus x. So we're going to write out the first 4 non-zero terms and the general term of the Maclaurin series expansion for this function and express the series using summation notation. Okay, so the way we do that, of course, is we're going to say, all right, our first function is just 1 minus x raised to the negative 1 power. That's equivalent to what we have right here, right? Because as we kick it down to the bottom and make it 1 over 1 minus x. Okay, so now we're going to take the first derivative of that. How many derivatives are we going to have to take? Well, we're doing the first 4 non-zero terms, So assuming none of them zero out, we're going to need 4 derivatives to do this. Well, we might need more or less. We'll just start with 4 and see how that goes. Okay, so we're going to take the derivative. -1 is going to come down in front. We're using the chain rule. Copy the inside function, subtract 1 from the power, multiply by the derivative of the inside function, which would be -1. So this is equivalent, -1 times -1, of course, would be +1, to 1 over the quantity 1 minus x squared in the denominator because of the negative power. Now our second derivative is, well, we want to think of this as like 1 minus x to the -2 power. So our -2 is going to come out in front, 1 minus x in the parentheses, subtract 1 from the power to get -3, multiply by the derivative of the inside function, -1. So -2 times -1 gives me +2 over the quantity 1 minus x cubed. And now I'm going to take the third derivative. So this is like 2 times the quantity, pardon me, 1 minus 3 cubed. So the 1 minus 3 to the negative, 1 minus x to the -3rd power. I apologize. So we're going to do -3 times 2, which will give us -6 out front. 1 minus x, subtract 1 from the power, so that's -4, and then multiply by the derivative of the inside function, which is -1. So this is 6 over the quantity 1 minus x raised to the 4th. And now we're going to need the fourth derivative. So this is going to be -4 times 6, which gives me -24 times 1 minus x to the -5th times the derivative of the inside function, -1. So I have 24 over the quantity 1 minus x to the 5th. Now I want to evaluate each of these for 0 because I'm doing a Maclaurin series. So the c value is 0. So I'm going to go f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and f quadruple prime of 0. And I'm going to work each of these out. So I have 1 over 1 minus 0, which is 1 divided by 1, which gives me 1. F prime of 0 is 1 over 1 minus 0 squared, so this is again equal to 1. The next one is 2 over the quantity 1 minus 0 cubed, so that's basically 2 divided by 1. And then I have 6 divided by 1 minus 0 to the 4th, which is 6. And then I have 24 over 1 minus 0 to the 5th, which is 24. So now I'm going to write out the first 4 non-zero terms of the Maclaurin series. So I start with f of c, which is f of 0, which is 1. And then my next term is f prime of 0, which is 1, times x minus 0. And then my next term is the second derivative evaluated at 0, which is 2, over 2 factorial times x minus 0 quantity squared, plus the third term is going, that was the third. The fourth term is going to be the third derivative, which is 6, evaluated at 0, which is 6, over 3 factorial times x minus 0 raised to the 3rd power. And then, let's see, we don't really need another term, do we? Because these aren't any of them going to zero out. So we're not going to actually need to use that fourth derivative. But we will have plus ... Because it's a series, it goes on forever. You can't just stop it like you did a polynomial, okay? So the terms are going to go like this. 1 plus x squared plus 3 factorial is 6, so this is just a coefficient of 1, x cubed, plus we have the first 4 non-zero terms. We need a general term. So the general term looks like it's going to be x raised to the nth power, 0, 1, 2, 3, plus dot, dot, dot. Remember to end with the plus dot, 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 because it's a series and it goes on forever. So there's the first 4 non-zero terms in the general term, so that's the first part of my answer. Then I also need it in sigma notation, summation notation. So I'm going to give the sum from n equals 0 to infinity of, let's see, x raised to the nth power. So there we go. Now this is a geometric series. The first term is 1 and the common ratio from term to term is x. So it is going to converge anytime x, the absolute value of x is less than 1. So just as a side note and an important thing to consider, the interval of convergence for this series is going to be from -1 to +1. X values from -1 to +1 will cause that series to converge. Okay, so that's that. Let's try another one. Number 2, we're going to do e to the x, which is a nice one to work with because derivatives of e to the x are pretty easy. First derivative, e to the x. Second derivative, e to the x. Third derivative, e to the x. I don't think these terms are going to zero out, so I'm just going to stop here. F of 0, f prime of 0, f double prime of 0, f triple prime of 0. So f of 0 is e to the 0, which is 1. Anything raised to the 0 power is 1. And then we have e to the 0, which is 1, e to the 0, which is 1, e to the 0, which is 1. So let's write out the terms of this Taylor series. It's going to be f of 0, which is 1, plus f prime of 0, which again is 1, times x minus 0, plus f double prime of 0, which again is 1, times, over 2 factorial, times x minus 0 squared, plus f triple prime of 0, which is 1, over 3 factorial times x minus 0 cubed, plus dot, dot, dot. So this is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. So it looks like the nth term would be x to the n divided by n factorial. Okay, and I mean, if you wanted to expand it out with the factorial values plugged in, we know 2 factorial is 2, and we know 3 factorial is 6. So that will simplify it just a little further. So this is the first 4 non-zero terms and the general term. The general term is the one with the n's in it. And then we need summation notation or sigma notation, the sum from n equals 0 to infinity of x to the n over n factorial. Okay. Now, it turns out if you do the ratio test for absolute convergence on this series, that the interval of convergence for this series is -infinity to +infinity. So it converges for all values of x. Let's move on to our third one. cosine of x. So we're going to have our first f of x is just cosine of x. The first derivative is going to be negative sine of x. The second derivative of negative sine of x is negative cosine of x. The third derivative of negative cosine of x is sine of x. Now, on the others, the third derivative seemed to be enough, but I want you to consider when you put in zeros to these values, cosine of 0, so that's just to the right on the unit circle, that's 1. But what about negative sine of 0? That's a y-coordinate. That's 0. So this term zeroes out, so we're going to have to go a little further here. F double prime of 0 is negative cosine of 0, so that's going to be negative 1. And then the F triple prime of 0 is sine of 0, which is 0. So we've really only got 2 non-zero terms right now. So we're going to have to go out further. So let's do the fourth derivative. Derivative of sine is cosine. And if I do the fourth derivative evaluated at 0, the cosine of 0 is equal to 1. So now I have 3 non-zero terms. Now let's do the fifth derivative. The derivative of cosine is negative sine of x. And the fifth derivative evaluated at 0, negative sine of 0. Uh-oh, another 0 term, so I still don't have 4 non-zero terms. Let's go to the sixth derivative. Negative cosine of x. You can see there's a pattern here, right? Cosine, negative cosine, sine. Cosine, negative cosine. The next one would be sine. Okay, so the sixth derivative evaluated at 0, negative cosine 0 is negative 1. So now we have 4 non-zero terms. So now we can finally stop. So we're going to have to go out to the power of 6 here on this particular Taylor or Maclaurin series, I guess, because we're putting in 0. So we're dealing with the Maclaurin series. So the first term is f of 0, which is 1, plus. The second term is f prime of 0, which is 0, times x. And then the third term is f double prime of 0, which is negative 1, over 2 factorial times x minus 0 squared, plus, now we're going to go to the third derivative, 0 over 3 factorial times x minus 0 cubed, plus, now we're doing the fourth derivative, which is 1 over 4 factorial times x minus 0 to the 4th power, plus the fifth derivative, 0 over 5 factorial times x minus 0 to the 5th, plus the sixth derivative, which is negative 1 over 6 factorial times x minus 0 to the 6th, plus dot, dot, dot. Okay, so what's going on here? Let's simplify things down just a little bit. We have 1. The 0 is going to go away, so we're going to have minus x squared over 2 factorial. This 0 term is going to go away. Then we have plus x to the 4th over 4 factorial. This 0 term is going to go away. Minus x to the 6th over 6 factorial plus dot, dot, dot. Now, can we come up with a general rule for this? Hang on, I believe I've made a... No, I didn't make a mistake. I'm sorry. I got confused. Can we come up with a general rule for this? Well, we can see this is an alternating series here. So we're going to have a negative 1. Now, this is the first term is positive. That's when n is 0. So if I raise it to the nth power, this is 0, so that would make that positive. This is 1, so that would make that negative. So that's good. We can do to the nth power. And then we've got over, well, let's see. The power on x is always even. So is it just 2 times n, 2 times 0, 2 times 1, 2 times 2, 2 times 3? Yes, so it's 2n. And then we're dividing by the same number as the power, so 2n in parentheses factorial. And then we'll have a plus dot dot dot. So there's our general rule. So here's the first 4 non-zero terms and the general rule that will produce the terms of this series. And now we need it in sigma notation. The sum from n equals 0 to infinity of -1 to the nth power x to the 2nth power over the quantity 2n factorial. And now let's talk about the interval of convergence. I'm not going to go through all the work for this. You're certainly welcome to do that on your own if you'd like. But the interval of convergence is from -infinity to +infinity. So for all real values of x, this series converges. All right, we have one more to kind of break down into the full Maclaurin series, which is the sine of x. All right, so like the cosine of x, we're probably going to have to go out further than just the first 3 derivatives, because when we plug in zeros, this being a Maclaurin series, it's centered at 0, we will have terms that zero out. So we already kind of know the pattern here. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And when we put in zeros, of course, we can do this quite a bit more quickly than we did last time because we just plugged zeros into all these values. So the sine of 0 is 0. So this one's going to zero out. The cosine of 0 is 1. Negative sine of 0 is 0. And negative cosine of 0 is -1. So far I only have 2 non-zero terms. So I'm going to do another derivative, the 4th derivative. And the derivative of negative cosine of x is the sine of x. So then the 4th derivative evaluated at 0 is the sine of 0, which is 0. So I still only have 2 non-zero terms. So I'm going to do the 5th derivative. Derivative of sine is cosine. And the 5th derivative evaluated at 0 is the cosine of 0, which is 1. So now I have 3 non-zero terms. So I think I'm going to have to do 2 more because the next one's going to zero out, isn't it? So negative sine of x, and then the 7th derivative is negative cosine of x. So the 6th derivative evaluated at 0 is negative sine of 0, which is 0. And the 7th derivative evaluated at 0 is negative cosine of 0, which is -1. Okay, so now we're going to write out the first 4 non-zero terms. Well, we're going to produce the Maclaurin series. So we start with f of 0, which is 0. And then we do f prime of 0, which is 1, times x. Plus, we do f double prime of 0, which is 0, over 2 factorial, times x squared. Then we're going to do the 3rd derivative evaluated at 0, which is -1 over 3 factorial times x cubed. plus, we're going to do the fourth derivative evaluated at 0, which is 0 over 4 factorial times x minus 0 to the fourth, plus 1 over 5 factorial times x minus 0 to the fifth, plus 0 over 6 factorial times x minus 0 to the sixth, plus negative 1 over 7 factorial times x minus 0 to the seventh, plus dot dot dot, because it goes on forever. So now I'm going to write out this series. We've got 0 plus x plus 0 minus 1 over 3 factorial times x cubed plus 0 plus 1 over 5 factorial times x to the fifth plus 0 minus 1 over 7 factorial times x to the seventh plus dot dot dot. Let's lose our 0 terms. We have x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot dot dot. We need a general term now. So the general term, it's an alternating series, so we're going to need a negative 1. Let's see, the first term is positive, just like it was on the cosine function, so I believe we can just raise it to the nth power, because when we put the 0 in for the first term, we'll have a positive, and when we put a 1 in for the second term, we'll have a negative. So that should get us our alternating sign correctly. Now we're going to have it multiplied by x raised to the power of. These are odd powers. So even though they increase by 2 each time, 2n is not going to do it. Remember, this is the 0th term, so if I do 2 times 0, that'd be x to the 0, which means there would be no x. But what if I do 2n plus 1 more? Then this would be 0 plugged in, would be 2 times 0 plus 1 gives me the first power. This is the first term, so 2 times 1 is 2 plus 1 more gives me 3. This is the second term, so 2 times 2 plus 1 more gives me 5. I believe this is going to work. And the number that we divide by is 2n plus 1 factorial, because the power matches the number that is the factorial is being applied to. So then we'll have plus dot dot dot. So here's my first 4 non-zero terms and the general term for the Maclaurin series, which represents the sine of x. And now we're going to write the general term. I'm sorry, we already did the general term. We're going to do the summation notation or sigma notation for this. The sum from n equals 0 to infinity of negative 1 to the nth power x to the 2n plus 1 power over the quantity 2n plus 1 factorial. And now the interval of convergence for this series is from negative infinity to positive infinity. Now, I took a good deal of time to go through the development of these 4 Maclaurin series for a very good reason. These 4 Maclaurin series must be memorized. On the AP exam, they are going to have some problems that have manipulations of series, which we're going to look at in great detail next time, like operations on series. And you need to know these by heart. Okay, so you need to put each one of these 4 on a note card. What is the Maclaurin series for 1 over 1 minus x? What is the Maclaurin series for e to the x? What is the Maclaurin series for cosine of x? And what is the Maclaurin series for the sine of x? And you need to be able to just produce those immediately without generating them out the way that we just did. Okay, so you're going to need to know the first 4 non-zero terms, the general term, sigma notation, and the interval of convergence for each of those. Okay? Now, if you are a person who really is good at memorizing things, it might be helpful if you know 1 over 1 plus x as well. It is 1 minus x plus x squared minus x cubed plus dot 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 plus negative 1 to the n times x to the n. And its interval of convergence is from negative 1 to 1. This is not required. You could generate this out if you needed it. Whoops, I forgot the plus dot 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 at the end. But it might be helpful if you know that. Also, the integral of 1 over 1 plus x dx is going to be the integral of 1 minus x plus x squared minus x cubed plus dot 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 plus negative 1 to the n x to the n plus dot 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 dx. So what is that going to give us? That's going to give us the natural log of 1 plus x, which is x minus 1/2 x squared plus 1/3 x cubed, just doing power rule backwards, minus 1/4 x to the 4th plus dot 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 plus negative 1 to the n x to the n plus 1 divided by n plus 1 plus dot dot dot. Okay, so this one and this one, which I generated by integrating that one. Okay, now those ones are not required. They are more just like, those come up fairly often too, but they are not the 4 that are listed as required memorized series for the AP exam. The first 4 that we did are. So you're going to need to know those for sure. Okay. Now, we are going to do a little bit more work with our Taylor series. Here's our example 5 for today. We're going to use the definition of Taylor series centered at C for the function. So for problem 5, those are our directions. F of x is given to be the sine of x, and C is going to be pi over 4. So we already know the first derivatives of this one, but we didn't center it at pi over 4. So let's consider if f of x is the sine of x, then we're going to do the sine of pi over 4. And the sine of pi over 4 from your unit circle, keep in mind that's the same as like a 45-degree angle. That's where the sine and the cosine are the same. It's going to be square root of 2 over 2. And then we have the first derivative. Derivative of sine is cosine, and the cosine of pi over 4 is square root of 2 over 2. And then we have the second derivative. Derivative of cosine is negative sine of pi over 4. So now we get negative square root of 2 over 2. And then we have the third derivative. Oops, I shouldn't be putting x here. I should be putting pi over 4 because I'm not plugging in x. I'm plugging in pi over 4. So I apologize for that inconsistency. So now I've got negative cosine of pi over 4, which is negative square root of 2 over 2. Okay. Now, we're going to put our first term, which is f of c, which is square root of 2 over 2. And then we're going to do our second term, which is f prime of c, so square root of 2 over 2 times x minus c, which is pi over 4. And then our third term is going to be f double prime of pi over 4, which is negative square root of 2 over 2, times x minus pi over 4 squared, and this should be divided by 2 factorial. And then the next one is going to be negative square root of 2 over 2 times x minus pi over 4 cubed divided by 3 factorial. And we already have 4 non-zero terms, so I'm just going to go plus dot dot dot. Now, we're also going to need a general term in sigma notation, okay? Notice every single term has a square root of 2 over 2 as a scalar multiple. We have a rule in series that we can pull a scalar multiple out in front of the sigma. So I'm going to say square root of 2 over 2 goes in front of my sigma from n equals 0 to infinity. Now, the alternating pattern for this series is really strange. It's positive, positive, negative, negative. Positive, positive, negative, negative. This is something you may not have encountered before. If you'd like an opportunity to try to predict how to make that happen, pause your video and give it a try. That is a little bit challenging, but I know I've had students in the past who've been able to come up with that, and I believe that there's probably some of you who can do that as well. So give yourself an opportunity to play around and see if you can come up with it, and then start your video again. I'm going to assume that you've had time to play with it, and I wish that I was there with you so that you could share your ideas with me. But since I'm not, I'm going to tell you how we can produce this pattern, positive, positive, negative, negative. Okay, so we need an even and an even, then an odd power on the -1. So the way we're going to do that is we're going to do n times n minus 1 over 2. So when you do 0 for the first one, that comes out to raising it to the 0 power, which is even. And then when you do 1, when you do the 1 minus 1 here, that becomes a 0, and that's also even. But then when you plug in a 2, you have 2 times 1, which is 2, then dividing by 2 gets you 1, which is an odd value. And when you sub in a 3, 3 times 2 divided by 2 is another odd, so that gives you your negative power as well. And it continues in that fashion. So now that I've shared this little trick with you, you may want to put that in your bag of tricks, in your little brain, that this could come up again. This may be something that you find useful to know, how to get a positive, positive, negative, negative pattern going on your series. So we've got that, and then it's going to be divided by n factorial times x minus pi over 4 raised to the nth power. So there's our summation notation representation of this Taylor series. Okay. Number 6. We're going to do a little proof here. And I'm not going to ask you to do one of these on the test, but I need you to keep thinking about these things. Prove that the Maclaurin series, I am going to do one like this in the homework, for the function f of x equals sine x converges to the function for all x. Okay, so what we're saying is this f of x equals the sine of x is going to equal the sum from n equals 0 to infinity of -1 to the nth power times x to the 2n plus 1 over the quantity 2n plus 1 factorial. Okay, that is always going to be the same. Now, how are we going to do this? Well, I want to use this Lagrange error-bound formula that I introduced to you previously, the remainder of a Taylor polynomial. We're going to pull this out of our bag of tricks. Again, This can appear on the AP exam. I would say that it's not tested with a great degree of frequency or a high number of points associated, but they like to keep you on your toes. So this is called the remainder of a Taylor polynomial, or also called Lagrange error bound. Okay, so this is like a note card that you should know if you want to be fully prepared for the AP exam. And we want to consider this function sine of x. The derivative of sine of x is one of, or the multiple derivatives. We go to cosine of x, negative sine x, and negative cosine of x. It's always going to be values no matter what your c value is, from -1 to +1. It can't be anything smaller than -1. It can't be anything greater than +1. So I'm going to put here, for our function f of x equals sine x, the absolute value of the nth derivative, or the n plus 1 derivative evaluated at z, will always be less than or equal to 1, because the nth derivative of x will always be either plus or minus the sine of x or plus or minus the cosine of x. So when we do the remainder, we always want to choose the biggest value this could possibly be. And we're going to say that the most it could be is 1 over n plus 1 factorial times x minus c to the n plus 1. Now, and we're doing this in absolute value bars because we're trying to figure out what the biggest value of the error could possibly be, the amount of remainder that we could have on this Taylor polynomial. Now we want to consider that the c value would be 0 because we're doing this for a Maclaurin series. It says so in the directions. So we're going to do what is the limit as n approaches infinity of, so this is x minus c, so that's just going to be x raised to the n plus 1 power over the quantity n plus 1 factorial. Okay, now as I send n to infinity, this is just polynomial values of x, and this is factorial values. So which one is growing faster? Okay, if you're not sure, why don't you graph them, the numerator and the denominator, in y equals in your calculator and take a look, because this is something that you should have an idea of growth rates. So the denominator is vastly outgrowing the numerator. So it's kind of like if you have the greater power in the denominator. This is going to approach 0 for any fixed value of x, because the factorial is growing more rapidly than the polynomial values, okay, that you see in the numerator. So since the remainder of x is approaching 0 as n approaches infinity, the Maclaurin series for the sine of x converges to the sine of x for all values of x. Okay? Now, you are going to have one like this in your homework. May or may not have to do maybe with a cosine, something very similar to this one, so it shouldn't be too far off from what you looked at in this example, but I'd like you to kind of get your feet wet with that just a little bit more in your assignment for practice. So, I have another note card for you about series for today. This is called the binomial series. And this is going to be the Maclaurin series for functions of the form 1 plus x raised to the k power. Okay, so I'm going to give you the rule, which is a note card for you to memorize, and then we're going to apply the rule to an example problem, and you will see some like this in your assignment as well. So here's the rule. We've got 1 plus kx plus k times k minus 1 times x squared over 2 factorial plus k times k minus 1 times k minus 2 times x cubed over 3 factorial plus dot 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 plus, we're going to go k times k minus 1 dot dot dot. This is kind of weird to have a dot 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 in the term itself. K minus the quantity n plus 1 times x raised to the nth power over n factorial plus dot dot dot. So, let's try this out for number 7. Use the binomial series to find the Maclaurin series for the function f of x equals the cube root of 1 plus x. So, what is the k value? The k value is the power on the 1 plus x, so it is the 1/3 power. So we're going to rewrite this as 1 plus x raised to the 1/3 power, so my k is equal to 1/3. Now I chose one with a fraction for k intentionally to do with you in class because I wanted to do one that was a little bit more challenging. You may have an easy one where the k value is something like 2 or, 5 or whatever. So, but it is possible for it also to be something like a fraction like 1/3. So we'll give this one a try together, and probably in your homework you'll see a little bit maybe of hopefully equal level of difficulty or easier level of difficulty for you to do on your own. So the first term is 1. That's super easy. The second term is k, which is 1/3 times x. And the third term is k, which is 1/3 times k minus 1. Okay, so if I take 1/3 and subtract 1 from it, that's going to give me negative 2/3. X squared over 2 factorial plus, next I have k, which is 1/3, times that same k minus 1, which we just got, negative 2/3, times k minus 2. So I subtract another 1 from the value that I have right here. Negative 2/3 minus 3/3 would be negative 5/3 over 3 factorial times x cubed plus dot 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 plus do I need to do another one? Or should I just, well, let's just stop here and let's kind of, actually I'm going to go one more. I apologize. Let's do the next one just so we can get a good pattern going. 1/3 times negative 2/3 times negative 5/3. Subtract another 1 from that. Negative 3/3 would make negative 8/3. thirds x to the fourth over 4 factorial plus dot dot dot. So let's try to, we're not going to fully simplify this, but we're going to simplify it down just enough so that we can write out the rule in sigma notation. So 1 plus 1/3 x plus, we have -2/9 x squared over 2 factorial plus, the next one is going to be 2 times 5 over, let's see, this was 3 squared, this is 3 cubed, x cubed over 3 factorial. And then we have plus 2, well actually it's going to be a negative this time, -2 times 5 times 8 over 3 to the 4th, x to the 4th over 4 factorial plus dot dot dot. Now, the interesting thing about this particular summation notation rule is that these first two terms are kind of an anomaly when it comes to the pattern that follows after that. So the way that we write this one out in sigma notation, which is kind of unique and new, is we're going to put 1 plus 1/3 x and then put plus our summation notation after that. And we're going to start with n equals 2 because the 0 term and the first term we're going to allow to precede the sigma notation. And it's going to go to infinity. Now we have signs alternating. The first term now here, when n is 2, is negative. So I'm going to have -1. I don't want to raise it to the nth term. I'm going to do the n-1 term, so that backs it up and makes it the first term come out a negative when I sub in a 2, because n is still 2 for this term. And then I'm going to have times 2 times 5 times dot 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 times, we need a rule that generates out the numbers that we're multiplying by here in the numerator, 2, 5, 8. This is a linear pattern. These are increasing by 3 each time. So we're going to do like a slope of 3n, but then when you plug in the 2, you get out the 2. So 3 times 2 is 6. We need to subtract 4 off of that, and that will get us to wherever we stop for whatever the n value is. And then we divide all of this by, we have powers of 3, 3 squared, 3 cubed, 3 to the 4th, so this is just 3 to the n, and then times n factorial, and then we have x raised to the nth power. So this is the general rule in sigma notation or summation notation for this binomial series. So you've got some more to practice with in your assignment on using that rule. This is probably the weirdest part because these numbers keep increasing how many you multiply by, but just look for the pattern and I think it should fall into place pretty easily for you. Don't be afraid either to look at the answer key to prompt yourself if you get stuck. That can help you to learn how to represent these rules in a general way. The more you look at them and analyze them, the better and more comfortable that you become in working with them on your own. Okay, I've got 2 more examples for you today to wrap things up. Number 8 says, find the first 4 non-zero terms of the Maclaurin series by multiplying. So I told you that you needed to memorize the Maclaurin series, the four Maclaurin or Taylor series that we looked at to begin with. E to the x cosine x. We're going to multiply e to the x times the cosine of x. So you do not want to have to generate those out by hand prior to doing the multiplication. On the AP exam, they select those four that I generated with you at the beginning of our notes today to be the ones that they do operations with on the AP exam. So they're expecting you to know them so that you can then show you know how to do operations on Maclaurin series with some that you have memorized, like these. So we know, or you will know after you study your note cards, that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, and it continues. And you will also know after you study your note cards that the cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot. So we have to make the first four non-zero terms by multiplying these two series together. How do we multiply them? Well, we're going to do old school multiplication just like you learned in elementary school. I'm going to write the first one on top, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot. And we're going to multiply that times, this is not an x, this is like the old school multiplication symbol, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot. Now, normally when you're in elementary school, you learn to multiply starting on the right side, but we can't do that this time because it goes on to the right forever. So we're going to start on the left side. So I'm going to start with this one, and I'm going to multiply it times each of the numbers on the top and list those out. So 1 times 1 is 1. 1 times x is plus x. 1 times x squared over 2 factorial is x squared over 2 factorial. Plus 1 times x cubed over 3 factorial is x cubed over 3 factorial. And now, how far out am I going to have to go? Because this could go on forever. You realize we're multiplying infinite values here. It says to do the first four non-zero terms, and sometimes terms will cancel out. So I wouldn't just write out 4. I would at least go one more than that. Okay, so I'm going to say, well, I know what the next value would be. It'd be x to the 4th over 4 factorial. And plus dot. Now, here's the thing. We're going to have to actually have numbers here instead of the factorials. So I'm going to change 2 factorial to 2, 3 factorial to 6, and 4 factorial to 24. Now, I've multiplied 1 times each of these numbers. Now I am going to move to the second value, negative x squared over 2 factorial, and multiply it times each of these values underneath, and then we're going to add them together, okay? So x squared over 2 factorial, this is negative x squared over 2 factorial times 1 is negative x squared over 2 factorial. And I'm going to write that lining up the powers of the x so that I'm combining like terms. So I'm going to have negative x squared over 2. And then I'm going to multiply this negative x squared over 2 factorial times the x. So that's going to give me negative x cubed over 2. And then I'm going to multiply negative x squared over 2 factorial times x squared over 2 factorial. So that's going to give me negative x to the 4th over, I have 2 factorial times 2 factorial, so that's 2 times 2, so that's 4. And now I'm going to add, okay, so we're going to go 1 brings down, x has nothing to add with it, comes down. X squared over 2 minus x squared over 2 adds up to 0. And this is one of the reasons why I wanted to go to one extra term, because we just had 1 0 out here. And then I've got, I need a common denominator here to add these fractions. So I'm going to multiply the one on the bottom times 3 over 3 so that I have a common denominator of 6. So I'm going to have over 6. I have x cubed minus 3x cubed, that's negative 2x cubed over 6. And then here I need a common denominator to add. So I'm going to multiply times 6 over 6 so that I have a common denominator of 24. And this is x to the 4th minus 6x to the 4th, which is negative 5x to the 4th. And this does continue. Okay, so now we've done the number 1 times each of these and the x squared over 2 factorial times each of these. So we're going to go to the next one and multiply and add again. Here's the thing. How do we know when to stop? Do we have to keep doing this forever? No, we need to keep going until we know we've completed the first 4 non-zero terms. And because right now my 4th term has an x to the 4th in it, I can't leave out this x to the 4th because it may be needed in order to combine with this x to the 4th term to complete my first 4 non-zero terms. So I'm going to take x to the 4th over 4 factorial, which of course is x to the 4th over 24, and multiply it times 1, which is going to be a positive x to the 4th over 24. And then when I go x to the 4th over 4 factorial times x, I now have x to the 5th, which I don't need if I'm going to stop at the first 4 non-zero terms. So I'm going to add vertically now. The 1 comes down, plus x, I don't need to write a 0 term, minus 2 6 simplifies to 1/3, so this is x cubed over 3. And then I have a common denominator already of 24 here, so I've got 24 on the bottom, negative 5x to the 4th plus 1x to the 4th. So we subtract and we get negative 4x to the 4th plus dot dot dot. Now that is not a simplified fraction, so I'm going to simplify it. So it's going to be negative x to the 4th over 6 plus dot dot dot. So this is the answer. This is the product of e to the x times the cosine of x, the first 4 non-zero terms. And it didn't ask us for a general term, it just asked us for the first 4 non-zero terms. So we are done at this point. All right, we learned how in elementary school to multiply, and then we learned how to divide. So this is our last example for today. We are going to find the first 3 non-zero terms in the Maclaurin series for the tangent of x by dividing. Now it doesn't tell us what to divide, but you remember how to write tangent of x as a quotient, don't you, from your pre-calculus? The tangent of x is equal to the sine of x divided by the cosine of x. And we know the rule for the Maclaurin series for the sine of x. That's one we're memorizing, so we can do operations with it. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, and so on and so forth. Actually, that would be a minus for that next term, wouldn't it? All divided by the rule for the cosine of x Maclaurin series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, dot, dot, dot. All right, so we're going to divide. Now, I'm going to make let's see, I'm going to skip 2 lines and then make my division bar so that I have room above for my answer. When you do division like this, top divided by bottom, the number that's on top is what goes under your division bar in old school elementary style division. So we have x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040 plus dot dot dot. And we're dividing by 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720. Okay, I don't know how far I'm going to have to go, but I need 3 non-zero terms. So I'm going to try to have 4 at least to start with in case something zeroes out. But if I just have 3 terms in my answer, that's going to be fine. So how do we divide this? The same way we did division back in elementary school. We say, what would we multiply a 1 by to give me this first number here? We don't care about anything following, just this first number, which is an x. You'd multiply a 1 times x, so the first term is x. Then you take x and you multiply it times each of these and you write it underneath and then you subtract. Okay, so x times 1 is x. X times negative x squared over 2 is negative x cubed over 2. X times x to the 4th over 24 is positive x to the 5th over 24. And x times negative x to the 6th over 720 is negative x to the 7th over 720. Okay, and now we're going to subtract. So x minus x is 0. That's gone. And now I've got to get a common denominator here, so I'm going to multiply this one times 3 over 3. So this is going to have a denominator of 6. So I've got negative 1x cubed plus, because minus negative is plus, 3x cubed. So negative 1 plus 3 is 2x cubed. Now I'm going to move to this term. I need a common denominator of 120, so I'm going to multiply my denominator times 5 over 5. Well, the fraction on the bottom times clever value of 1, 5 over 5, so that we have the common denominator of 120. So now I have 1x to the 5th minus 5x to the 5th, which gives me negative 4x to the 5th. And now I'm going to go to the next term. I need a common denominator of 5040, so I'm going to multiply the fraction on the bottom times 7 over 7. And now I've got 5040 as the denominator, negative x to the 7th plus 7x to the 7th is 6x to the 7th. And that's positive. So I'm going to simplify these fractions before I continue. This is 1/3, so x cubed over 3 minus x to the 5th over 4 goes into 120 30 times plus x to the 7th, 6 goes into 5040, 840 times. All right. Now we start the process over again. What would you multiply a 1 by to give you x cubed over 3? Well, that would be x cubed over 3. And now we multiply that times each of these numbers, write them underneath, and subtract. X cubed over 3 times 1 is x cubed over 3. X cubed over 3 times negative x squared over 2 is x. We add the powers, 2 plus 3 is 5, so x to the 5th over 2 times 3 on the denominator is 6. And then we're going to have x cubed over 3 times x to the 4th over 24. So that's plus x to the 7th over 24 times 3, which is 72. And then minus dot dot dot. I'm going to subtract. So we're going to go x cubed over 3 minus x cubed over 3. This is 0. I need a common denominator to subtract here, so I'm going to have to multiply the bottom fraction times 5 over 5. So I'm going to have a denominator of 30. Negative x to the 5th over 30 plus 5x to the 5th over 30 is 4x to the 5th. And then I've got, let's see, am I going to need to do another one? I don't need to go out to x to the 7th. No, I'm not going to need that term. I just need to simplify this one. So it's going to be 2x to the 5th over 15. So then I ask myself, what would I multiply 1 by to give me a 2x to the 5th over 15? 2x to the 5th over 15. And I have the first 3 non-zero terms in the Maclaurin series representing the tangent of x. And that is the end. Okay, that was pretty heavy. We are in the thick of it right now, but I have faith in you and I know that you can do this. What you need to do is take it slow and easy and be patient with yourself. Don't expect perfection. Check your answers as you go. Look for your mistakes. Work with a study buddy. Make a friend from class if you haven't already. I sure hope you have. But put your heads together. The learning process is better done with a buddy. That is not only true in high school, but also in college. It's a good habit to get into. If you haven't made a friend, reach out and make a friend. And let me know if you need help. Come in for tutoring. Call me, email me, whatever you need to do. But let's get in touch and make sure that you are feeling comfortable with all of this. Memorize your 4 Maclaurin series, the 1 over 1 minus x, the geometric one, e to the x, sine x, cosine x. You've got to know those, and that's going to help you a lot. And keep at it. We're getting there. We're almost through with this unit. So I look forward to seeing you next time. Have a wonderful day. Bye for now.